There are already reports of as many as 30 tremors across the Bay Area, according to the U.S. Geological Survey. Let's show you where this is happening. It's a 4.2 magnitude quake, according to USGS.
The warning came fast. Earlier this week, NOAA issued a tsunami warning covering roughly 500 miles of Northern California coastline. People moved toward high ground. Coastal routes cleared. Emergency systems lit up. Then, less than an hour later, the warning was cancelled. The closest dart buoy had barely registered above background noise. Measured waves at sea level stations did not exceed 10 centimeters. The ocean had answered, and its answer was small. But here is the thing worth paying attention to. The warning ending is not the story. What the instruments kept recording afterward is: why did seismic activity keep reorganizing across a much wider area than the rupture zone? And what does it mean when stress moves not just through one fault, but across connected boundaries at a junction where three plates meet? To understand that, you have to go to the geometry. The Mendocino Triple Junction sits off the coast of Cape Mendocino in Humboldt County. And it is best understood as a mechanical problem before it is understood as a danger. Three boundaries converge here, and each one moves differently. The Mendocino Fault is a right lateral transform fault running between the Pacific Plate and the Gorda Plate. The San Andreas is the right lateral transform between the Pacific and North American plates. And the Cascadia Subduction Zone is where the Gorda Plate dives beneath North America. One boundary slides, one dives, one tears. The forces acting at each boundary are not independent. They share a corner, and stress changes at that corner propagate outward along all three edges. That geometry is why a single offshore earthquake here is never entirely local. The main shock that started this sequence hit in the early evening. USGS coordinates placed it on the Mendocino Transform Fault System at a depth consistent with strike-slip rupture. The shaking was widely felt across Northern California. BART temporarily halted service. EarthScope documented roughly 5 million shake alert-powered alerts sent across the region. In Humboldt County, utility disruptions were reported, and field assessments noted some structural damage in the Eel River Valley. No casualties were confirmed. For a magnitude 7.0 on a well-monitored fault system, the outcome was serious but bounded. What came next is what makes this sequence worth examining carefully. Most people track aftershocks as a number, a count that ticks upward and eventually slows. That framing misses the more important variable, which is where the activity spreads, not just how many events accumulate. Within the first few days, EarthScope had catalogued nearly 100 aftershocks above magnitude 3.0. And the sequence has since grown to hundreds of catalogued events, with no sign of stopping. Normal aftershock sequences decay roughly according to Maury's law, with frequency dropping as a predictable function of time. What seismologists are watching here is not just the rate, it is the map. And the map is spreading in directions that warrant a closer read. The Temblor analysis of the sequence identified aftershock clusters along the Mendocino Fault itself, which is expected. But it also identified roughly 15 aftershocks well east of the rupture zone, extending toward the junction where the San Andreas Fault merges into the Mendocino system. This is the area where the boundary type changes, where the transform fault of the San Andreas connects to the transform fault of the Mendocino, and where stress from an offshore rupture has a geometric pathway into the continental fault network. This is not fault-to-fault communication in any mystical sense. It is stress transfer, a mechanical process in which a rupture on one fault changes the loading conditions on nearby faults by redistributing the forces that were keeping them locked. Some patches receive added stress, some receive reduced stress. The ones that matter for future risk are the ones that were already close to their failure threshold, and just received a nudge in the wrong direction. The clearest single example of dynamic triggering in the sequence came from Clear Lake. Temblor reported a magnitude 4.3 event near Clear Lake approximately 3 minutes after the main shock. 3 minutes is too fast for static stress transfer, which travels at tectonic timescales. What 3 minutes suggests is dynamic triggering, where the passing seismic waves from the main shock temporarily disturb a fault patch that was already under stress. The waves pass through, the patch slips, and a small earthquake results. This is well documented in the seismological literature, and it is the most defensible explanation for what happened near Clear Lake. It is presented here as possible triggering because the data supports that interpretation without requiring certainty. The stress transfer calculations that Temblor published for the larger fault systems nearby carry their own important caveats. And those caveats are part of the story, not a footnote. Their Coulomb stress analysis estimated roughly 0.25 bars of increased stress at the northern tip of the San Andreas and roughly 0.25 bars at the southern tip of the Cascadia megathrust. To place that number in context, a prior magnitude 6.4 Ferndale earthquake had already contributed a similar increment. The combined effect of those two sequences suggests that roughly a 40-kilometer section where the San Andreas merges into the Mendocino Fault is now somewhere between 0.25 and 0.5 bar closer to failure than it was just a few years ago. That does not imply imminence. Stress changes are real and measurable. The timing of any resulting earthquake is not knowable. This region has produced sequences like this before, and the historical record is instructive. Rewind to April 1992. A magnitude 7.2 thrust earthquake ruptured beneath the area near Petrolia. Earthscope summarizes the aftermath as roughly 1 meter of shoreline uplift, a 1.1 meter tsunami measured at Crescent City, injuries, and significant damage. The USGS report on that sequence describes 3 strong earthquakes within 24 hours, with the magnitude 6.5 and 6.6 aftershocks occurring on different fault planes than the main shock, indicating stress transfer between mechanisms and not just a long strike continuation of the same rupture. Over the following week, more than 2,000 aftershocks extended across multiple fault systems within the Pacific and Gorda Plates. The lesson from 1992 is specific and still applicable today. This region can mix fault mechanisms, produce a locally generated tsunami, and generate aftershock fields that spread across connected boundaries. The current sequence is not without historical context. It is, in some respects, an echo with far more instruments watching. The most recent scientific work on this rupture adds detail that was not available in the first days after the event. Researchers found that the rupture initiated at depth between roughly 20 and 30 kilometers and propagated unilaterally up dip and eastward. Early aftershocks tracked the rupture direction, and the pattern is consistent with strong static stress transfer loading the eastern end of the fault and the junction zone. This is not infection. It is propagation and mechanical loading, and the distinction matters because it points to where scientists are focused right now. If you live in coastal Northern California and you process this sequence in real time, the most useful thing the initial warning demonstrated is how fast the system works and how fast it can be corrected. The warning was issued quickly. It was cancelled within roughly 1 hour when the data showed no significant tsunami generation. The measured waves were small. The protocol worked as designed. For anyone in a coastal zone, the practical guidance is unchanged. Follow official alerts in the moment, have a planned route to high ground, keep a go-bag current, and register for local alert apps. The warning system speed in both directions, up and down, is a feature, not a failure. What the sequence leaves behind is not a prediction. It is a live case study in how a geometrically complex tectonic junction redistributes stress across multiple fault systems over time. What has changed is how finely we can now observe it. The rupture depth, the propagation direction, the stress increments on neighboring faults, the dynamic triggering at Clear Lake. all of it is traceable in a way it was not in 1992. When the aftershock cloud starts drawing lines toward major fault junctions, the question becomes, which faults are receiving enough stress to cross the threshold, and how close were they already? We are tracking that as the data develops. Like and subscribe for the follow-up, and watch the next video to see what the fault map looks like right now.